Hello students, welcome to this lecture one introduction to trigonometry. So in this lecture we will discuss introduction of trigonometry. Okay, so here we'll discuss introduction first, then we'll discuss trigonometric ratios, and then we'll see some examples related to this. So let's get started. So student, you have already studied about triangles and in particular right triangles in your earlier classes. Okay, so let us take some examples from our surroundings where right triangles can be imagined to be formed. So here we take some examples. Okay, so there we observe right triangles. Okay, so let us see here now. Question number one, example number one. Here we suppose the students of a school are visiting Qutub Minar. Okay, Qutub Minar. Now, if a student is looking at the top of the Minar, a right triangle can be imagined to be made. Okay, so as shown in figure 8.1. So this is figure 8.1. So here you can see one student who is seeing the top of the Qutub Minar. Okay, and here this made to be made a right angle triangle. So can the student find out the height of the minar without actually measuring it? So we actually have known about the Pythagoras theorem. So we know Pythagoras theorem applicable for right angle triangle. So here it made to be a right angle triangle. So we can here use Pythagoras theorem and we can find out the height of the minar. Okay, so in this chapter basically we'll learn about some trigonometric ratios actually that will help you to find the height of this triangle. Okay, so let us see one more example. So in next example, here we suppose a girl is sitting on the balcony of her house located on the bank of a river. She is looking down at a flower pot placed on a stair of a temple situated nearly on the other bank of the river. Okay, so a right triangle is imagined to be made in this situation as shown in figure 8.2. So this is figure 8.2. So here you can imagine this is actually a right angle triangle. Okay, so if you know the height at which the person is sitting, can you find the width of the river? So basically here we have to find the width of the river. Okay, so we know this height where the person is sitting. Okay, so we know this height and we need to find this. So here you can imagine to be made a right angle triangle in this situation. Okay, so now you can use Pythagoras theorem and you can find the width of the river. Okay, so let us see example 3. So in example 3 here we suppose a hot air balloon is flying in the air. Okay, so a girl happens to spot the balloon in the sky and runs to her mother to tell her about it. So her mother rolls out of the house to look at the balloon. Now when the girl had spotted the balloon initially, it was at point A. Okay, so it was at point A. And when both the mother and daughter came out to see it, it had already traveled to another point B. Okay, so now can you find the altitude of B from the ground? So can we find this? This is by can we find the altitude of B from the ground? Okay, so yes, we can find the altitude of B from the ground. So basically for finding the altitude of B from the ground, here we have to use some trigonometric ratios. Okay, so in this lecture we will discuss about some trigonometric ratios in our later section. Okay, so in all the situation given above, here we have given 3 examples. Okay, so in all the situation given above, the distances or heights can be found by using some mathematical techniques which come under a branch of mathematics called trigonometry. Okay, so this all this situation given above, the distances or heights can be found by using some mathematical techniques, and these techniques basically come under a branch of trigonometry. Okay, so the word, what do you mean by the word trigonometry? So here if we split this odd trigon and metron. Okay, so here this odd is derived from the Greek odds, tri meaning 3, gon meaning sides, and metron meaning measure. Okay, so in fact trigonometry is the study of relationships between the sides and angles of a triangle. Okay, so the earliest known org on trigonometry was recorded in Egypt and Babylon. So early astronomers use it to find out the distances of the stars and planets from the earth. Okay, so basically trigonometry meaning tri meaning 3, gon meaning sides, and metron meaning measure. Okay, so in fact trigonometry is the study of relationship between the sides and the angles of a triangle. Okay, so the application of trigonometry, so early astronomers use it to find out the distances of the stars and the planets from the earth. Okay, so now let us even today most of the technology advanced methods used in engineering and physical sciences are based on trigonometric concepts. Okay, so based on trigonometric concept, most of the technology advanced methods used in engineering and physical sciences. So in this chapter we will study some ratios of the sides of a right triangle with respect to acute angles. Okay, so called trigonometric ratios of the angle, and we will restrict our discussion to acute angles only. Here we will restrict to our discussion to acute angles only. Okay, so here we will only discuss one acute angles. However, these ratios can be extended to other angles also. Okay, so we can also extend these ratios to other angles like obtuse angles. Okay, so we will also define the trigonometric ratios for angles of measure 0 degree and 90 degree. So we will calculate trigonometric ratios for some specific angles and establish some identities involving these ratios called trigonometric identities. Okay, so in this chapter basically we will study about some ratios of the ratios of trigonometric function. Okay, so some ratios of the sides of a right angle triangle with respect to acute angle. So here basically we will restrict our discussion to acute angle, but you can be extended to other angles like obtuse angle. Okay, so here we'll also define the trigonometric ratios for angles of measure 0 degree and 90 degree, and then we'll see some trigonometric identities that actually established by trigonometric ratios. Okay, so these are our these topics we'll discuss in this chapter. Okay, so now here we'll see trigonometric ratios. Okay, so here we introduce trigonometric ratio first. So before starting trigonometry, you should see this figure. So this is actually a triangle. Okay, so ABC is a triangle. Here, this side is called side adjacent to angle A. Okay, and this side is called side opposite to angle A. So this is angle A. So this side is adjacent to angle A, and this side is opposite to angle A. And this is hypotenuse. Okay, so this is hypotenuse. So in section 8.1, you have seen some right triangles imagined to be formed in different situations. Okay, so let us take a right triangle ABC here, that is shown in figure 8.4. Okay, so here this is a right triangle. So now here angle CAB, this angle or brief angle, in brief angle CAB, that means this angle. Okay, so in short, this is angle A. So is an acute angle. Okay, so note that the position of the side BC with respect to angle A, okay, and it faces angle A, we call it the side opposite to angle A. Okay, and AC, this is called the hypotenuse of the right triangle, and the side AB is part of angle A. So side AB is a adjacent of the angle A, at the side of the adjacent of the angle A. So we call it is the side adjacent to angle A, and note that the position of the sides change when you consider angle C in place of A. Okay, so if we change the angle, the position of the side change when we consider angle C in place of angle A. Okay, so now let us see. You have studied the concept of ratio in your earlier classes. Okay, so we now define certain ratios involving the sides of a right triangle and call them trigonometric ratios. Okay, so the trigonometric ratios of the angle A in right triangle ABC, that is shown in figure 8.4, are defined as follows. Sine of angle A, this is equal to sine opposite to angle A, side opposite to angle A, divided by hypotenuse. So if we see the figure 8.4, then there the side opposite to angle A, that is basically BC. Okay, and the hypotenuse, that is basically AC. Okay, so now cosine of angle A, this is basically equal to side adjacent to angle A, that is AB, and divided by hypotenuse, that is AC. Okay, and then tangent of angle A, this is equal to side opposite to angle A divided by side adjacent to angle A, and this is equal to BC over AB. And cosecant of angle A, this is equal to 1 over sine of angle A. So we know sine of angle A, that is actually side opposite to angle A divided by hypotenuse, that is equal to BC over AC. Okay, so 1 over sine of angle A, that is actually cosecant of angle A, that is equal to hypotenuse divided by side opposite to angle A. So this is equal to AC over BC. And now secant of angle A, this is actually reciprocal of the cosine of angle A. So secant of angle A, this is equal to 1 by cosine of angle A. So we know cosine of angle A, that is equal to side adjacent to angle A divided by hypotenuse. Okay, so 1 over cosine of angle A, this is equal to hypotenuse divided by side of adjacent to angle A. So this is equal to AC over AB. And now cotangent of angle A, this is equal to actually reciprocal of tangent of angle A. Okay, and we know tangent of angle A, this is equal to side opposite to angle A divided by side adjacent to angle A. Okay, so now 1 over tangent of angle A, this is basically equal to side adjacent to angle A divided by side opposite to angle A, that is equal to AB over BC. So here the ratios defined above are abbreviated as sine A, cos A, tan A, cosec A, sec A, and cot A respectively. Okay, so here note it down. The ratios cosec A, sec A, and cot A are respectively the reciprocals of the ratios sin A, cos A, and tan A. Okay, so also observe that tan A, this is equal to BC over AB, and you can also write it as BC over AC divided by AB over AC. Okay, so BC over AC, this is basically equal to sine of angle A. Okay, and AB over AC, this is equal to cos of angle A. So BC over AC, this is equal to sine A, and AB over AC, this is cos A. So this is equal to sine A divided by cos A. And cot A, this is equal to cot A, this is equal to AB over BC. So you can write AB over BC as AB over AC divided by BC over AC. That is actually equal to cos A by sin A. So the trigonometric ratios of an acute angle in a right triangle express the relationship between the angle and the length of its sides. Okay, so here trigonometric ratios mainly express the relationship between the angle of this right angle triangle and its length of its sides. Okay, so why don't you try to define the trigonometric ratio for angle C in the right triangle? Okay, so here question, why do not you try to define the trigonometric ratios for angle C in right triangle? That is shown in figure 8.5. So now here the first use of the idea of sine in the way we use it today was in the work of Aryabhatta by Aryabhatta in 500 AD. Okay, so Aryabhatta used the word ardhajya for the half chord, which was shortened to jya or jiva in due course. Okay, when the Aryabhatian was translated into Arabic, the word jiva was written as it is, and the word jiva was translated into sinus, which means curve. Okay, when the Arabic version was translated into Latin, soon the word sinus, also used as sine, become common in mathematical texts throughout Europe. Okay, so an English professor of astronomy, Edmund Gunter, first used the abbreviated notation sin. Okay, so the origin of the terms cosine and tangent was much later. The cosine function arose from the need to compute the sine of the complementary angle. Okay, so for finding the complementary angle of sine function, we needed cosine function. So Aryabhatta called it cotija. The name cosinus originated with Edmund Gunter in 1674. The English mathematician Sir Jonas Murray first used the abbreviated notation COS. Okay, so now here one remark, note that the symbol sin A used as an abbreviated for the sine of the angle A. Okay, so sin A is not the product of sine and A. This is actually abbreviated of the sine of angle A. Okay, so sine of angle A, this is equal to side of the opposite of the angle A divided by hypotenuse. So sine separated from A has no meaning. Similarly, cos A is not the product of cos and A. Similarly, interpretations follow the other trigonometric ratios for like tan A, cosec A, sec A. Okay, so now if we take a point P on the hypotenuse, so this is our hypotenuse AC, this is our hypotenuse. If we take a point P here, okay, so now or a point Q1 AC, okay, then actually one AC extended of the right triangle ABC, and draw PM perpendicular to AB side and QN perpendicular to AB extended side. Okay, how will the trigonometric ratios of angle A in triangle PAM differ from those of angle A in triangle CAB, or from those of angle A in triangle QAN. Okay, so let us see. To answer this, first look at these triangles. Is triangle PAM similar to triangle CAB? So we have studied in our chapter 6 when two triangles is called similar triangles, that we have learned in our previous lecture. Okay, so to answer this, we first look at these triangles. Triangle PAM, and is triangle PAM similar to triangle CAB? So here from chapter 6, recall the angle similarity criteria. Using the criteria, you will see that the triangles PAM and triangle CAB are actually similar triangles. Okay, so therefore, by the property of similar triangles, their corresponding sides of the triangles are proportional. So we have AM divided by AB is equal to AP divided by AC. This is equal to MP divided by BC. Okay, so this is this hold, since their corresponding sides of the triangle, two similar triangles are proportional. So from this we find MP by AP, this is equal to BC by AC, and we know BC by AC is equal to sine of angle A, sine A. Similarly, AM by AP, this is equal to AB by AC, and here AB by AC is equal to cosine of A. Okay, and MP by AM, this is equal to BC by AB, and BC by AB is equal to tan of A, and so on. This shows that the trigonometric ratios of angle A in triangle PAM not differ from those of angle A in triangle CAB. So in the same way, you should check that the value of sine A and also other trigonometric ratios remains the same in triangle QAN also. Okay, so from our observations, it is now clear that the values of trigonometric ratios of an angle do not vary with the length of the sides of the triangle if the angle remains the same. Okay, so if angle remains same, then trigonometric ratios of the angle do not vary with the length of the sides. Okay, so here we note it down. For the sake of convenience, we may write sine square A, cos square A, etc. in place of sine A whole square, cos A whole square, etc. respectively. But cosec A, this is equal to sine A whole inverse, but does not equal to sine inverse A. Okay, so note it down. Cosec A, this is equal to actually reciprocal of sine function A, reciprocal of sine A, but it does not equal to inverse function of sine A. Okay, so this does not equal to sine inverse A. So it is called the sine inverse of A. So sine inverse A has a different meaning, which will be discussed in your higher classes. So similar conventions hold for the other trigonometric ratios as well. Sometimes the Greek letter theta is also used to denote an angle. Okay, so for denoting angle, we in generally use the Greek letter theta. So we have defined 6 trigonometric ratios of an acute angle, and if we know any one of the ratios, then can we obtain the other ratios? Okay, so let us see. So if we have any one ratios, then can we find any other ratios? So if in a right triangle ABC, here we have given sine A, this is equal to 1 by 3. Then this means that the opposite side of the opposite of the angle A, that is BC, divided by hypotenuse AC, this is equal to 1 by 3. That is the length of the sides BC and AC of the triangle ABC are in the ratio 1:3. Okay, so you can see this figure. So if BC is equal to K, then AC will be equal to 3K. Okay, so K is any positive integers. So to determine other, here we need to find the value of AB. So now from figure 8.7, trigonometric ratios for the angle A, we need to find the length of the third side AB. So do you remember the Pythagoras theorem? So for finding the length of the side AB, you can use the Pythagoras theorem. Okay, so let us use it to determine the required length AB. So we know Pythagoras theorem, hypotenuse square plus side of the adjacent of the angle A square plus side of the opposite of the angle A square. Okay, so here length of AB square, this is equal to AC square minus BC square. And here we have given, we have hypotenuse AC is equal to 3K and the BC is equal to K. Okay, so this is equal to 3K whole square minus K square, and this is equal to 8K square. So you can write it as 2 times root 2K times 2 times root 2K whole square. So therefore the length of AB is equal to plus minus 2 times root 2K. So we know length cannot be negative, so here we can take only the value AB is equal to plus 2 times root 2K. Okay, since AB actually length of AB is not negative, so cannot be negative, so AB can only 2 times root 2K. Okay, so now cos A, this is equal to actually AB divided by AC, and here AB is equal to 2 times root 2K and AC is equal to 3K. Okay, so this is equal to 2 times root 2 by 3. So similarly, you can find the other trigonometry ratios, like you can find tan A. So tan A is equal to here the height is the side opposite of the angle A is BC and the side of the adjacent of the angle A is AB. So BC by AB. So tangent of A, this is equal to BC by AB. So here the value of BC is equal to K and value of AB is equal to 2 times root 2K. 2 times root 2K, and this is equal to 1 by 2 times root 2. Okay, so tan A is equal to 1 by 2 times root 2. So you can similarly find the other trigonometry ratios of the angle A. So if we have given a value of ratio, value of the ratio, then you can easily find other trigonometric ratios of the angle A. Okay, so now here remark, since the hypotenuse is the longest side in a right triangle, then the value of sin A cos A is always less than 1, or in particular equal to 1. So the value of sin A cos A is always less than equal to 1. So now let us explore some examples on trigonometric ratios. Okay, so in first example, here we have given tan A, this is equal to 4 by 3. And here we have to find the other trigonometric ratios of the angle A. Okay, so tan A is equal to 4 by 3, that is given to us. So let us see how to find other trigonometric ratios. So let us first draw a right triangle ABC, that is shown is figure 8.8. So this is our right triangle ABC. Okay, so here given, we know that tan A, this is equal to BC over AB. Okay, so this is equal to 4 by 3. So therefore here BC and AB, they are in ratio 4:3. So we can let BC is equal to 4K and AB is equal to 3K, where K is a positive number. Now by using the Pythagoras theorem, we have AC square, this is equal to AB square plus BC square. Okay, so AC square is equal to 4K whole square plus 3K whole square, that is equal to 25K square. So AC is equal to 5K. So the length of AC is equal to 5K. So now we can write all the trigonometry ratios using their definition. So we know sin A is equal to BC over AC, and the value of BC is equal to 4K, and the value of AC is equal to 5K. So this is equal to 4 by 5. And cosine of A, this is equal to AB by AC. This is equal to 3K by 5K, that is equal to 3 by 5. Okay, so therefore cot A is equal to, we know, the reciprocal of tan A, that is equal to 3 by 4. And cosec of A, that is actually reciprocal of the sin A. So we know sin of A is equal to 4 by 5. So cosec of A is equal to 5 by 4. and we know sec A, that this is reciprocal of the cos A. So we have find the value of cos A is equal to 3 by 5. So sec A is equal to 1 by cos A, that is equal to 5 by 3. Okay, so now let us see next example. So here in next example, if angle B and angle Q are the acute angles such that sin B is equal to sin Q, then prove that angle B is equal to angle Q. Okay, so let us prove it. So here let us consider two right triangles ABC and PQR. So here we consider two right angles. So where sin B is equal to sin Q. Okay, so we have sin B is equal to AC over AB, and sin Q is equal to PR over PQ. Okay, so then AC over AB divided by PQ over PR over PQ. So therefore here we can let AC over PR is equal to AB by PQ is equal to K. Okay, so by now using Pythagoras theorem, here BC is equal to square root of AB square minus AC square, and QR is equal to square root of PQ square minus PR square. Okay, so now BC over QR, this is equal to square root of AB square minus AC square divided by square root of PQ square minus PR square. Okay, and this is equal to square root of K square PQ square minus K square PR square divided by square root of PQ square minus PR square, and this is equal to K times square root of PQ square minus PR square by square root of PQ square minus PR square, and this is equal to K. So I'm naming this 2. And now from equation 1 and 2, we have AC over PR is equal to AB by PQ is equal to BC by QR. So then by using theorem 6.4, here triangle ACB, this is similar to triangle PRQ that you have studied in our chapter 6. Okay, so therefore angle B is equal to angle Q. So student, I stop here this lecture. Thank you very much to all of you.